So, I'm going to cover the short questions from chapter 11. So, let's begin. What is meant by inertial frame of reference and a non-inertial frame of reference? Now, what inertial frame of reference means is that you're describing the position of an object from a place where your body is at rest, or it is at constant or uniform motion. Okay, so it basically stays at rest or is in uniform motion. It obeys the Newton's first law of motion, which is inertial law, in which a body at rest stays at rest and a body in motion continues its state of motion unless acted upon by another force. So that is the inertial frame of reference. Now, the examples of inertial frame of reference are Earth is approximately an inertial frame of reference because objects on Earth obey the law of Newton, but Earth itself is not an inertial frame of reference. It is a non-inertial frame of reference because it is accelerating because it's spinning around the sun. Another example would be a car moving with uniform velocity on a straight road, train at steady velocity. These are the examples. Now, non-inertial frame of reference would be a body which is accelerating, crazy bumpy ride, and for example the car suddenly stops or hit the brakes, or for example the lift suddenly stops, or when the plane is taking off. Those kind of in such situations the laws of Newton do not apply without introducing pseudo forces. Okay, so those are inertial and non-inertial frame of references. A frame of reference in which Newton's law holds true either at rest or moving with constant velocity. All laws of bear same in its inertial states. A non-inertial is that frame of reference that is accelerating. Newton's law do not hold. Objects appear to move even without any real force acting upon them. That is important. Earth is approximately inertial. It revolves around Sun. Its acceleration is negligible for most forces. In non-inertial frame, we introduce imaginary forces like centrifugal forces to explain the observed motion. Inertial frames are equivalent for describing physical laws, which means that you do not prefer one inertial frame over another. All are equal. Like, I can perform an experiment at rest and it would be same as doing an experiment in a moving train. I would not prefer the results of one over another. Now, the second one is, what are two postulates of special theory of relativity? Now, what Einstein said was, the laws of physics are same in all inertial frame of references. Now, I just explained it in the earlier question, but it basically means that the physics works the same no matter how fast you're moving, unless you're not accelerating or changing speed, or even if you're at rest. So that is the first postulate. There is no absolute rest or motion. And the second one is principle of constancy of light. The speed of light in free space is always the same for all observers, regardless of the motion of the source or observer. For example, this basically means that the speed of light is constant, which is different from, contradictory from, or opposes the normal laws which usually means that, for example, if I'm driving a car and I throw a ball at a speed of 10 kilometers per hour, and I'm driving the car with a speed of 50 kilometers per hour, the total speed of the car or the ball would be 60 kilometers per hour. Adding the speed of the car plus the speed by which I threw it outside. For an observer outside the car, I threw it at 60 kilometers per hour, which is the normal thing that happens usually. The velocities add up, but for light, this does not happen. The speed of light is same whether you're flying at the speed of a rocket or you're just staying at rest. So if I turn on a laser beam while being in a rocket ship and you turn on a laser beam being in a rocket ship, the speed of light would be the same for both of us, right? So this basically means that if the speed of light is same, then something else has to give. What that means is that the length of the rocket ship in the direction in which it is moving will shrink, or the time will pass slowly for the rocket ship because it is moving fast. Okay, so this basically means, but also we do not observe such increase in mass or change in time because we are not speeding that much as much we would be if we were traveling at the speed of light. So that is the thing. Okay, so let's get a little bit formal with it. All laws of physics are same in all inertial states of references. No inertial frame is preferred over another. Experiments performed in different inertial state yield identical results. There is no way to detect absolute motion. Okay, the speed of light in vacuum has the same value in all inertial frames regardless of the motion or of the source or observers. Light does not obey classical velocity addition rule. Whether the source is too far away from you, the light speed remains constant. This contradicts common sense but has experimentally verified. From these postulates, Einstein derived time dilation, length contraction, mass variation, relativity of stimuli events simultaneous for one observer might not be for another observer. Mass energy equivalence, which means that changes in mass require large amounts of energy, and this also means that if an object is traveling very fast, then its mass increases, and at a time it would require a very large sum of forces to move it further, to push it further. So in that scenario, to change its speed would require large amounts of energy because its mass has increased. So it means that with the increase of speed, mass increases. When mass increases, the requirement to move the mass further increases. So you could say that we need large amounts of energy to change the mass of an object. Okay, so now the next question is, why is it impossible for a material particle to move with the speed of light? Okay, so when you move a toy car, initially it is very easy to move it, but let's imagine in ideal conditions you could move it as farther as you could. Now when you're moving it farther than while it's already moving, you would notice that the amount of energy required to move it further has increased because its mass has increased, and the mass has been converted into kinetic energy. The kinetic energy has been converted into mass because you're moving the mass, you're pushing it with your kinetic energy. This kinetic energy adds up to the mass, so the mass increases, it becomes heavier. So in order to move it further, you can't just do that because you would need very big amount of energy. You could see it is written here that 50% of light speed you wait a bit more harder to accelerate. 90% of light speed you weigh double. 99% of light speed you weigh 7 times heavier. And 100% of light waves you weigh infinite, so you will need infinite amount of energy, which is practically impossible. So that's why you cannot move at the speed of light. So that is the answer. Now the thing with light is that light does not have mass, so can move light can move at the speed it is moving, which is referenced as the speed of light naturally. So it does not need energy to move because it does not have mass. Also, at the speed of light, the length would become zero, the mass would become infinite, and the time would become infinitely slow. So that is just practically impossible. Anyways, next question. What is meant by what is meant by proper time and proper length? Now, proper time is the time that exists at an inertial state, and proper length is the length that exists at an inertial state. Basically means that proper time is the time interval measured by an observer who is at rest relative to the events happening. If you're riding a car and you measure some time in the car, you have proper time. If you're at rest, you measure some time, that is the proper time. That does not involve acceleration to its observer. Proper length similarly is the same thing. Proper length is the length measured by an observer who is at rest relative to the object. Okay. The time runs slower in such states where the body is in non-inertial frame and the length becomes shorter. For example, you measure a minute on Earth at ground and another person measures a minute while in being aeroplane. You would see that your time is more than the time that the person on the airplane has observed. Why? Because the person was moving faster. Kind of mind-bending, isn't it? So basically, that is the thing. And then we have a little bit formal stuff. The time interval between two events measured by an observer who is at rest relative to the events. The events occur at the same position in the observer's frame of reference. It is the shortest time. Okay, there is a notable thing. It is the shortest time interval because the time increases in non-inertial states, and for length, the length is the maximum length because the length decreases in non-inertial states. This also shows us time dilation because time dilation means that time slows down in non-inertial states and length contracts in non-inertial frames. So that is the thing. Next question is, what is relativistic mass length in time? If an object is moving with speed v, then its mass increases. The relation between proper mass m naught and relativistic mass. So what is relativistic mass? This basically means that when you move at the speed of light, you get heavier. There is relativistic mass. relative to the normal mass at initial state. You get heavier, so that means the relativistic mass. You get the length becomes shorter compared to the length at inertial state, so that is relativistic length. The time slows down at speed of light, and at a high acceleration speed, so that means there's a relativistic time. So at 99% light speed, you would weigh as much as a car if you weigh 30 kg at inertial states. At 99.9% of light speed, you would weigh you would be as thin uh, as paper if you were 4 feet tall. And you can read that you would basically, anyways, let's go at the next question. Let's get a little formal. Relativistic quantities refer to the measurements of mass, length, time observed from a frame of reference moving at relativistic speeds. These quantities differ from their rest values due to effects predicted by Einstein's special theory of relativity. The mass of an object when it is moving at relativistic speed is called relativistic mass. The length of an object measured in the direction it is moving at a high speed is called relativistic length. The next question is, why does mass of a moving object increases? So this is an interesting one. According to the special of relativity, the mass of an object is varying quantity. It depends upon the speed of the moving object. Rest mass, when the mass is at rest, then it is m0, it is called rest mass. So basically what happens is that when you push a mass in a direction, you're using your kinetic energy to move the mass in a specific direction, or if the mass runs in a specific direction by using some sort of energy, like for example a car or a plane. So the kinetic energy adds up to the mass and the mass gets heavier. Okay, that basically means that energy and mass are the same thing in different forms. You're using your energy to move the mass. That energy converts in a way that adds up to the quantity of mass. So that is basically the thing. You address your normal mass, you start running, you have movement energy. The movement energy adds a tiny bit to your mass. At normal speed, it's so tiny, you never notice it. At near light speed, it becomes huge. That's it. According to the Einstein's special theory of relativity, the mass of an object increases with its velocity due to mass energy equivalence principle. The reason is explained below. The Einstein famous equation E is equal to mc squared shows that energy and mass are equivalent. Energy can be converted into mass and vice versa. When an object moves, it gains kinetic energy. This kinetic energy manifests an increase in mass. Okay, so that's it. Then you have some formulas and shit. I'm not gonna go over them. Mass increases due to kinetic energy. Mass increases with velocity. As it approaches to the speed of light, it becomes harder to change its mass. So that is there. at CERN, something happened that they charged a particle so much that its speed became 99.99% of the speed of light. So it became very difficult to change its path. So they needed very huge amounts of magnets that had very much too much energy to spin the path of these particles, even though they were small, tiny particles. Next question is, explain that the speed of light is an ultimate limit for any object. Think of it like this: the universe has a speed limit posted everywhere. That speed limit is 300,000 kilometers per second, and unlike the highway speed limits, this one is absolute. No one can break it. Why? At 100 kilometers per hour, moving a mass is easy. At 500, it gets harder. 1000, engine straining. 100 kilometers, car is getting heavier. At 29999, the car weighs as much as a mountain. At speed of light, it becomes infinite. So you cannot exceed that limit because you do not have enough energy to move it past the limit of light, because it just weighs infinite. So that is the thing. So the three reasons are, you get infinitely heavy, you need infinite energy, time goes crazy, time would stop at speed of light. Only massless particles can approach speed of light, which is light itself. Photon particles, electron particles, these kind of. Wait. Photon particles, electrons cannot. Massless photon, gravitons, yes, they can. The last one is, give example where the results of theory of relativity have been verified. So this one is a bit technical. Einstein said, time slows down, lengths get shorter, mass becomes heavier when you go really fast. People thought it can't be possible. The first example is GPS satellites. Your phone GPS tells you exactly where you are. GPS satellites outside the Earth move at the velocity of 14,000 kilometers per hour. They are also farther from the Earth's gravity. Einstein said, time runs slowly for fast things. So that means that GPS moves. The time for GPS moves slow. If the time for GPS moved as much as it was on Earth, you would have been in another city. Like, the difference of a location would be 10,000 kilometers. And this doesn't really happen, so that proves that Einstein was correct. The second one is particle accelerations. I already explained it, so that it's for short questions. I hope you can understand it. And the next would be constructive response questions and long questions. Bye.